Good afternoon. So today we will talk about the second major equation that we will deal with in this chapter, the wave equation. And as I mentioned before, the heat equation and the wave equation will be our default examples to learn the techniques of solving these type of boundary value problems. The wave equation, I choose actually to describe it in a much more simplified version than in the book. We're going to use the configuration in the book, but for the purpose of just deriving the equation, I prefer to use a model which is even more simplified than in the book, because it's a little bit analogous or similar to the one we used in the ordinary differential equation class when we talked about the mass spring system. So some of the stuff that you might remember from mass spring systems equations in the ordinary differential equation class might come to play here, basically. I mean, you might see some connections. We need to go over a couple of preliminary stuff. So first of all, this will be the one-dimensional wave equation, in which the object in question is a vibrating string. So basically a string that has some sort of elasticity in the material, such that, you know, if you deform it or if you bend it, it can oscillate due to the elastic or forces in that string. So in the differential equation class, we used a spring basically with an object of a certain mass attached to it. For the purpose of this lesson, the wave equation, imagine the vibrating string being made of infinitely many objects, all of them at a single point, essentially, you know, along the length of the object of the string. And the springs essentially are just replaced by really nothing. Like this, you know, the string itself can bend and pulsate, for instance, you know, if you deform it. So we're going to get to that in a minute. And again, for simplicity in the beginning, we just assume that the motion of this string is governed just by the elastic force or the spring force. So remember that the second law of motion states that the resultant force is the mass times the acceleration. So if you have a point that moves, its acceleration is related to the resultant force, all the forces essentially that act on that point, and the mass of that point, the mass of the object at that point. And another important physical law is the Hooke's law, which states that the spring force or the elastic force is a constant times displacement of that point. This depends, the constant as always, on the nature of the material, and it can change from point to point on the material, but again, to make it simpler in the beginning, we just assume that it is a constant. So what is going to be the dependent variable? So what are we going to establish a PDE for? Well, imagine you have this string. So suppose this is the string of length big L, and it's not going to be overly important at this point, but you can imagine that the left end point is at x equals 0 coordinate, and this is just along the x-axis. So this will be the right end point of the string, and therefore the domain for the space variable is going to be 0 and L. And here is where I'm going to deviate a little bit from the book, because the book says that you can basically deform the spring vertically, so you can bend it up or down, and then you let it loose to oscillate, so the displacement will be a vertical displacement. Just to make it easier, assume that the string, this vibrating string can only vibrate horizontally. So basically you can stretch it or compress it, right, left and right, both ways and sideways. But anyway, so all the deformation happens horizontally. I just basically want to deal only with the displacement along the x-axis and not to worry about angles, essentially, if I have to take into account the deformation over in a vertical plane, right, over along the y-axis. So with that in mind, then the dependent variable for which we're going to establish the PDE is going to be, to use the notation in the book, is going to be y of xt, which will be the displacement of the point x at time t. So because this string can stretch left and right, each point can be displaced from its equilibrium position. So the displacement of the point x at time t from the equilibrium position. So basically, if y of xt is 0, that means there is no tension, right, at that point. It's neither a stretch nor compress around that point. You really have to imagine that point is basically surrounded left and right by two very, very small strings, essentially. And in fact, the way I'm going to derive the wave equation is to illustrate it by imagining this string as made of several points where the mass is concentrated with springs of negligible weight, essentially, of mass between them. This is basically the way I'm going to derive the equation. So this is similar to the ordinary differential equation class, if you remember, except now it doesn't depend on the time only, it depends on the position of the object. So it's like having really infinitely many masses attached to springs all together, not just one single mass and a single spring like in the ODE class. And also by convention, very important so you can understand what comes later, if displacement is to the right, then we're gonna assign by convention the positive sign to the displacement. So positive displacement means that it is to the right. And if displacement is to the left, then the value of that displacement is less than 0. So for example, let's say you have two nearby points at coordinates x1, x2. And let's say you stretch it like that. x2 moves to this point, x1 moves to a left point. Basically, what you want to say in this case is that the displacement at the point x2 is positive because it's stretched to the right, and the displacement at the point x1 is negative. So if you imagine that in between these 2 points, there's like a spring with no other mass in between, the overall stretch of the spring comes from the displacement of the 2 objects that are attached to that spring. So notice it's a cumulative thing here, because if this moves to the right and this one to the left, it's the overall stretch is actually y of x2t minus y of x1t. This is a little bit confusing sometimes in the beginning, but this is really like a double negative. So let's say, for instance, that y of x2t is 5 and y of x1t, the point on the left, is minus 3, right? A negative stretch. Stands to reason that the overall spring stretches by 8 inches or whatever the measure unit is. So that's why you have to subtract the 2. You always have to subtract essentially the displacement of the right endpoint and then minus the displacement of the left endpoint because of this convention: positive to the right, negative to the left. And then the overall stretch again is going to be bigger. This should be pretty obvious, right? I mean, if you stretch it in opposite directions, the 2 displacements should somehow compound each other, right? I mean, 5 inches and 3 inches should become 8 inches. By the same token, since we are on this topic, let's say you have a point x1 here and then a point x2, then let's say x2 moves to the right by, I don't know, let's say 3 inches, and x1 moves also to the right by 1 inch. So the two displacements are both positive. So the one at x2 is 3, the one at x1 is plus 1 because both are to the right. But notice that the stretch on the left endpoint kind of takes away from the tension created by the right endpoint. So the overall stretch in the spring is still the difference between the two. But it's going to be 3 minus 1 in this case. Yeah, so you move the point x2 to the right, but if the point on the left moves also to the right, that takes away some of the stretch created by the right endpoint. So I'm taking this detour here just to make sure, and you can pause a little bit and imagine these scenarios, but to understand the equation later, it's important to understand why I always take this difference, displacement of the right point minus this displacement of the left endpoint. It's all about the convention that we make here with the positive displacement to the right and then negative to the left. All right, so let's go back to other assumptions we make here before we move on to actually establishing the equation, which is not actually difficult, but the preparation is a little bit more tedious. So in order to establish the equation of motion, so basically an equation for this displacement, let's suppose the string is approximated, this string of length m, L. So let's say the string is approximated by n points where the weight is, where the mass is distributed, equally spaced. I'll show a picture on the next page here. So to start with, the overall string, so the original string has length, as I mentioned before, L. Let's say also it has the mass given by big M, and the spring constant, which comes into the Hooke's law, big K, and let's say that's constant for the entire spring. That's the capacity of the spring of the string. I'm sorry, to stretch. It's depending on the nature of the material. It tells you how easy or hard it is for the string to stretch. So these are the three physical constants attached to our string that will vibrate left or right. And we're going to approximate essentially this string by imagining that, like I said, the mass is essentially distributed over n equally spaced points. As you might imagine a little bit later, we're going to take a limit, and then this n will go to infinity essentially, so that we can establish the equation for the whole vibrating string. So I'm going to do it on the second page, this approximation. So what I'm going to do, I'm going to take again this string of length L, or wire of length L, and I'm going to split it into n equal parts, just like a partition essentially. And we imagine that the entire mass, like I said, is going to be evenly distributed over these points, so that in between the 2 points, we can imagine that it's like a spring of negligible weight. Right, so all the weight is concentrated on these equally spaced points. So let's stay tuned for the next page to show you the picture. All right, so take a moment to write this down and keep in mind again the main assumptions that I wrote on the right corner here. I mean the main quantities relevant to the wire. So we have the length big L, we have the mass, the total mass of the whole wire or string, and K is the spring constant for the whole string. And then, like I said, imagine we split this into n equal pieces where the mass is concentrated. So n equal pieces of mass little m. So that means, imagine that the in between these points we have essentially little springs that are of negligible weight. Now, because we split big L into n equal pieces, the equally spaced, right? The distance between each nearby pieces is gonna be big L over n. So let's denote this distance by little h. And that means the relationship between h and big L is that little h is big L over n, or in other words, big L is n times h, or if you want little h, well, I wrote that already, L over n. So little n also can be written as big L over h. We're going to need these relationships later. That's why I wrote them here. So you split big L into n equal pieces. That means the distance between between two nearby pieces is little h. So we're going to focus on three nearby points here in the middle. So suppose the coordinate of the point here is going to be x. So this is the x coordinate, the position of that point. Therefore, the next one to the right is going to be at x plus h. And then the one further to the right is at the coordinate x plus 2h. We're going to derive essentially a formula for the equation of motion for the object in the middle, the one at position x plus h. Another important thing to understand here is that each of these little springs between two nearby points will have a higher constant, spring constant. So imagine intuitively, what's harder to stretch, a long wire or a short one? So I mean, if you have a wire of length L and big K denotes the spring constant of that big wire, if instead of stretching it from both ends, you take two much closer points to each other, two nearby points, then you should intuitively understand that the spring constant gets higher. It's going to be harder to stretch the spring if you pull it from two nearby points. So in fact, the spring constant between two nearby points, because you split this string into n pieces, the spring constant is going to be little k n times the big constant, so n times k. This is again a little bit counterintuitive, but pause for a moment and again, just imagine you basically play with this string, right? You pull it from both ends, from 0 to L. How easy it is to do that is given like this big K. As you split this into n equal pieces, it's going to be n times harder to basically stretch it in the same manner if you pull it from two much closer points. So that's why the spring constant between two nearby points is higher, n times higher essentially than the original spring constant. Now notice that the relationship h will be important later. So if little k is equal to n big K, now remember little n was big L over h. So big L times k over h is yet another way to write down the spring constant for each of these little springs. What about the mass? Did I say something? No, I didn't say. So the little mass m, again, the relationship between the big mass of the entire string, since you split it into n equal parts, then little m is big M over n. On the other hand, little n was L over h. And if you simplify this, this is going to be m times h over L. So let's keep this in mind as well. This is the relationship between the spring constant, the little mass of a little point, and little h. The importance of writing this is because eventually, as you might guess, we're going to let h go to 0, because that will essentially approach the whole string, right? I mean, with h goes to 0, n goes to infinity, so basically you have infinitely many points that form the entire vibrating string. Okay. So with that in mind, I think we are close to the moment when we write the equation of motion for the object at the coordinate x plus h. So we're going to look at that point at coordinate x plus h, And notice that as these points move left and right, so imagine this whole string is in motion, there will be two forces acting on this point. A force that comes from the right hand side, let's call it F right, and another force which is in the opposite direction that acts on the left side. It's always in the opposite direction if you think about it, again, because of the convention of positive motion to the right, negative to the left. If there is a motion to the right, that means the string on the left is going to act in the opposite way as the motion and vice versa. So if I look at the object here at coordinate x plus h, that's surrounded by two strings, and those two strings are going to be connected to two more points, right? The one at x plus 2h over here, and the other one at coordinate x over here. Okay, so with that in mind, and remembering that the Hooke's law states that, let's state it again, the Hooke's law states that the elastic force is the mass times displacement. Then the equation of motion for this point is the following. So on the left, I'm going to write the acceleration, which, remember, it's going to be the mass times the second derivative with respect to t at the point x plus h and time t. So the double derivative with respect to t is the acceleration. And on the right hand side is the force acting on the right side of the object minus the force that acts on the left side. Okay, so for the force acting on the right hand side, you can take a look at the top of the page if you want as well, right? That force acting on the right is governed by the motion of the two objects at position x plus h and x plus 2h. So that spring will have a certain stretch or compress, a certain displacement caused by the displacements of those two objects. So that's going to be the spring constant, little k, times the displacement of the object to the right. So that means y of x plus 2h t minus the displacement of the object to the left, which is at position x plus h. Remember on the previous page why you always subtract the displacement from the right object. So displacement of the right object minus the displacement of the left object. That's the overall displacement of that spring, which is multiplied by little k. Minus the force on the left side, which is again spring constant. And again, starting with the object on the right side, so it's going to be y of x plus h t, displacement of that object, minus displacement of the one on the left, which is y of xt. Okay, so at this point, I'm going to move the divide by m both sides. So we're going to have y partial twice with respect to t, x plus ht. And we're going to factor big, I'm going to keep these actually like that, but I'm going to factor k. So it's going to be little k over little m. And let's keep these two separated. So we have y of x plus 2h, comma t, minus y of x plus h, comma t, minus y of x plus ht, minus y of xt. Okay, what is this k over m after all? Let's take a moment and rewrite this in terms of h. So little k over m, little k, remember, is big L, big K over little h, divided, let's write it like that, so divided by little m, which is big M times h over L. So if I simplify this, this is going to be LK over little h times L over M times H. And let's combine these constants, L squared big K over big M times 1 over H squared. So this constant replaces little k over m. The key thing is to look at this H squared, because we're going to take a limit immediately as H goes to 0. So we're going to have a big constant, a chunk here that is a combination of these physical constants that are specific to the original string, right? It's total mass, it's total length, it's elastic constant, big K. And then we're going to divide this big parenthesis to H squared. So my equation so far is y partial t twice equals L squared K over big M. This will be renamed later by a different constant. Divided by, on the top we have y of x plus 2h comma t minus y of x plus h comma t, and then minus y of x plus h comma t minus y of xt over h squared. All right, as h approaches 0, this big chain rule, this big difference quotient here, this big quantity on the right, is in fact the definition of the partial derivative with respect to x twice. Is the definition of the second derivative with respect to x. If you want a quick intuitive understanding why that's the case, in fact, we're going to write it on the right hand side. So I'm going to write it in a more expanded form just to see that it's the difference quotient of two derivatives. So hence it's the second derivative with respect to x. So we're going to write the whole thing on the next page by dividing the top to h and then the whole thing to h again. In practice, again, we're going to make this L squared bk over m another constant. It's customary to denote it by a squared, because that denotes a positive constant, and when you solve it, when you solve the equation, it's much more convenient to denote that constant by a squared. You'll see it later on why that's the case. But any renotation will do as long as you realize that this is going to be basically a positive constant. So let's stay tuned for to finish up this on the next page. Okay, so we don't need to do this, as I said in the previous page, because what I obtained in the previous page on the right hand side, that is, as h goes to 0, the definition of the second derivative with respect to x. But I want to show you intuitively why that's the case. So that over h squared is the key thing. If we distribute that over h squared in this fashion, so 1 over h for the two difference quotients that you see on the top, and another one over h, as h goes to 0, you can imagine the top. So basically, if you look at the first difference quotient, that will be basically partial x at the point x plus h. Look carefully here, it's x plus h plus another h, x plus h over here on the second term, divided by h. So that's essentially approaching partial x at x plus h. This one here is going to be partial x at the point xt. So x plus h and t here, right? These are partial with respect to x. And then if you further divide it to the h, that's a difference quotient of the partial x. So basically this will finally approach partial x twice at the point xt. So, and then of course on the left hand side, as h goes to 0, this approaches partial y with respect to t twice at the same point. All right, so when everything is said and done, y partial t twice at the point xt is some positive constant that depends on those physical properties of the object, partial x twice at the point xt. In short, of course, we can write it like that. So that's the wave equation when there is no risk of confusion. So we don't have to always specify of xt all the time when it's clear from the context. So This was essentially the simplest possible derivation of this equation. Now, to really visualize it a little bit better, in our class, so from now on, y of xt will denote the vertical displacement. And the convention is going to be y of xt is going to be positive if above the equilibrium position, and y of xt negative if below the equilibrium position. So the reason it's easier to visualize is because typically in many problems you will imagine, for example, let's say a string attached to two poles. Let's say you have something like that. These are poles. And then you have a string that is, let's say, stretched, not stretched, laid down horizontally when it is not tensioned. And then you're going to have, for example, some initial deformation or stretch, and then you let it loose, and then it will vibrate up and down. And a positive displacement will be, for example, for a point here is going to be y of xt will be positive. For a point over here, that is corresponding to that dip, that's going to be a negative displacement. So you can show, and you can look in the book, the derivation of the equation leads to the same equation. It's still the one-dimensional equation, but it's just a little bit more tedious to show, to prove, basically. So that's why I chose the left and right oscillations, essentially. The equation is still the same. So notice that the only difference between this and the heat equation is that, mathematically, of course, the only difference is that on the left side you have not the first derivative with respect to t, but the second partial with respect to t, second order derivative with respect to t. The right-hand side is again the Laplacian, just like in the first, just like in the heat equation. So we're going to deal primarily with the one-dimensional heat equation, wave equation, but I'll show you on the next page the versions in 2 and 3 dimensions and what they actually represent. One thing I still want to talk about here is that, again, this equation involves only the motion generated by the spring force, the elastic force. So that makes it essentially a homogeneous PDE. But you could have other external forces. So for example, as you will see in a homework problem, in fact, if you, for example, consider the weight as well that hangs on the object. So if the weight is not negligible, then you could have a wave equation which is not homogeneous, because in addition to all the components which are caused by the spring force, you could have also the weight. G stands for the gravity. The G is the gravitational acceleration. Again, it's with the negative sign because it points always downward. So then the wave equation, of course, contains more terms like this. Now remember, G in the pounds, feet pounds, this is 32. I think it's, what is it? Feet square per second, I think. I forgot the units. And then in the metric system, this is going to be 9.8 feet per second squared, actually, meter per second squared. So 32 or 98. But it'll appear with a negative sign in the wave equation because it points downward. So I think I'm gonna have one more page just to discuss possible boundary conditions, and I think that's it for today. All right, so in one dimension, as I said before, you have a vibrating string. The wave equation looks like this. In 2 dimensions, imagine you have essentially a bouncing surface, like the one that kids play when they jump up and down. Then in that case, of course, the displacement will be depending on two space variables and the time t. The equation will be yt partial t twice, a squared y partial x twice plus y partial, actually, let me actually use a different dependent variable, because I can't use really little y. I want to use x, y, z. So let's say u of x, y, t is the displacement. So in that case, the wave equation will be like this. I want to point out the right hand side is the Laplacian, just like in the heat equation. Or in 3D, you can have some 3D object and imagine that it's pulsating or vibrates along the normal vector, like a pulsating sphere. And in that case, of course, the displacement will be depend on 3 points, x, y, z, and the time t. And then the wave equation will be given by this: u partial t twice, a squared times the Laplacian. So in general, the wave equation is the second derivative with respect to t equals a constant times the Laplacian. All right. Well, I think we'll talk about the static waves next time. I think the last thing I want to mention is how do boundary conditions may look like. There's a lot of variety here, and we will have time to go over lots of examples with respect to this. But one thing to keep in mind is that typically we need to specify at the very least the initial displacement. So let's say in the one-dimensional case, when you look at partial t twice equals a squared partial x twice, initial displacement will be obviously the original deformation at time 0. So that is a typically is a function of x. And then in addition to that, you typically need also the initial velocity, which means y with respect partial t at x0. And that could be another function, g of x. If, for example, you deform the string and let it loose, that means the initial velocity is 0. But in order to solve the problem, you typically need two conditions like this. Unlike in the heat equation in which you needed, let's say, the initial temperature, usually you need three initial conditions for problems like this. Boundary conditions depend on other assumptions that you make on the string. Let's say, for example, that you have two poles where the string is attached to. So for example, at the position 0, you have a fixed pole of height 5, and then at position L, you have a pole of height 12. And let's say that your string is attached to these two poles, may be deformed initially in this manner. You know, that deformation is going to be given by the function f of x, but at all times t, you have some restrictions, in the sense that restrictions or boundary conditions, in the sense that the points attached to the poles won't move. So in that case, you have essentially an initial displacement, if you want, that is there forever, right? So for example, you would have y of 0t equals 5, y of lt equals 12. So that means those 2 points are fixed, no matter how much the other the whole string vibrates up and down, right? So the endpoints left and right are at two fixed values. And there are variations of this. For example, you could have one point moving up or down along a pole, like for example, a point that can move. There is an interesting problem actually in the homework that I'll talk about later on. And so these are the typical boundary conditions essentially. You could also have an infinite string in the sense that it's so long that for all practical purposes, you don't care what happens at its endpoints. You look at the motion somewhere in the middle and you don't have essentially other boundary conditions. So I think that's it for today. I'll see you next time.